In this video, we discuss inverse functions. We'll talk about properties of inverse functions, finding an appropriate restriction so that f has an inverse, and then determining visually whether f has an inverse. Let's say we're given f of x equals 3x to the fifth plus 2. And we'd like to find the inverse function. Traditionally, the way that we would do that is we would replace f of x with y, and then switch the roles of x and y. And then after we do that, we try to get y by itself. So we subtract 2 from both sides. Oops, there should be a 3 there. And then I divide by 3. And then to get rid of that fifth power, I take the fifth root. And so then we have y equals x minus 2 divided by 3 raised to the 1/5. And then it's tradition to replace that y with f of x, or f inverse of x, excuse me. And so this is a typical problem statement. And one of the effects of using this process to find f inverse is that f inverse is a function that will undo everything that f initially did. So here's the beginning of our list of properties. Inverse functions undo each other. And I think we can see why that's the case. If the inverse function is found in this way, this function is definitely going to undo everything that this function did. I replaced f of x with y, and then I switched the roles of x and y, and then I tried to get y by itself. So what I had over here was 3y to the fifth plus 2, and I was trying to isolate that y. How do we isolate that y? Well, the last thing that we did to x was we added 2 in order to get y by itself. Now to get to the x, or to get to this y, in order to get rid of that addition of 2, we have to subtract 2 from both sides. And then we say, okay, I've got a 3y to the fifth. How do I get rid of the multiplication by 3? Well, I divide by 3. And then I see how do I get rid of the fifth power? I raise both sides to the 1/5 power, and so I get this. So it makes a lot of sense that this would be the inverse function of this. As you think about what we did to x, and then what we did to x here and what we're doing to x here, this says take x, raise it to the fifth power, multiply by 3, and then add 2. This says take x, subtract 2, divide by 3, and then raise it to the 1/5 power. The claim is that those functions undo each other. And so I think it makes sense when you think about the fact that multiplication and division are inverse operations. Addition and subtraction are inverse operations. Raising something to the fifth power and taking the fifth root are inverse operations. So these functions undo each other. Algebraically, we can show that this way. F of f inverse should be x, and f inverse of f should be x. Because if I apply f inverse first, and then I apply f, well, since this is undoing this, I should just get the original expression back. And the same is true if we do it the other way around. So we can check that this function is actually the inverse function of this one by substituting this function into this one. So my f of x was 3 times x to the fifth plus 2. And now I want to substitute or replace x with f inverse of x, which happens to be x minus 2 divided by 3 raised to the 1/5 power. So if I put that into here and simplify it, hopefully I'll get x. If I take the fifth root of something and I raise it to the fifth power, those undo each other. And then I have this expression times 3, the 3's undo each other. And then I have x minus 2, and then the plus 2, those undo each other. and I just get x. So we see that f of f inverse is x, and f inverse of f of x is f inverse evaluated at f of x, which actually I don't need very large parentheses here. F of x is actually 3x to the 5th plus 2. F inverse is x minus 2 divided by 3 raised to the 1/5 power. So if I replace x with 3x to the 5th plus 2, those operations undo each other. This operation will undo that one. And then the x to the 5th raised to the 1/5 power is just x. So we see that the functions undo each other. And so f of f inverse gives us x, and f inverse of f gives us x, which is consistent with this idea that addition is the inverse operation of subtraction and vice versa, and multiplication and division undo each other, and raising something to a power and then taking the appropriate root, corresponding root, they undo each other as well. Now, because of the nature of this, because of what we did, in order to get f inverse, we switched the roles of x and y. The domain of f is the range of f inverse. So all of the x values for that we put into f become the y values of f inverse, and vice versa. The range of f is equal to the domain of f inverse. And I think that that makes sense because we switched the roles of x and y. Consistent with that, when we graph f, the point AB is on the graph of f. When the point BA is on the graph of f inverse. And then finally, if we want to determine visually whether a function has an inverse, we use what's called the horizontal line test. The horizontal line test just says that every horizontal line, well, actually, if every horizontal line crosses the graph of f only once, then f has an inverse. And if f has an inverse, we say that it's 1-to-1. Let's say the function is 1-to-1. And all that means is that every x has only one y, and every y has only one x. We don't have any y values that have multiple x values. Every x has only one y for every function, but every y, or there are possibilities for functions where we can have a y value that has more than one x. Those are not allowed when we're talking about inverse functions. So let's look at a graph on Desmos.com and confirm some of these things visually. In particular, we're going to look at this function. Okay, so this is our function, f of x equals 3x cubed plus 2. And we can see visually that it passes the horizontal line test by just graphing a horizontal line and then thinking about what happens as that horizontal line moves up and down. That horizontal line only crosses once. And no matter where for every horizontal line that's possible, it only crosses the graph once. So that function has an inverse. Here's an example of one that doesn't have an inverse. If I move this horizontal line to the interval, looks like between like 2 point something and that sort of negative 2 point something, looks like maybe negative 2.2, 2.3, and positive 2.2 or 3, something in there like that, like 2.5 actually, according to the the calculator for Desmos for the equation of that line. So if my y value is between about negative 2.5 and positive 2.5, look at my horizontal line crosses more than one time, or crosses the graph more than once. I've got, when y is equal to 0.5, we get 3 different x values. This x value, or the x value that corresponds to that point, and that point. And that's true for all of these y values in here in this interval. Now, when y is greater than 2.5, we're fine. And when y is less than negative 2.5, we're fine. But on this interval, we have problems. The horizontal line crosses the graph more than once. So this function does not have an inverse. Another function that does not have an inverse is y equals x squared. You might think, well, that's a problem because we need to be able to undo squaring something. Well, we can take the square root, but that's, and that is the inverse of this function, but we aren't able to use that all the time. We can only take the square root of the number if that number is positive. So what we do when we want to make a function like y equals x squared invertible is we take a restriction of that function. We say, if I only looked at the left side of this parabola, I'd be fine, and the function would have an inverse. Or if I only looked at the right side of this parabola, I'd be fine, and the function would have an inverse. So either way, if I make a restriction to positive values for x, now my function has an inverse because the horizontal line only crosses once. Or if I say, I'm okay with negative values, the horizontal line also only crosses once. As long as we make that choice, then the function has an inverse, and that inverse for the positive branch, where x is positive, is a positive square root of x. All right, so we've got that. Now we said that inverse functions undo each other and that this was the inverse of, or this function down here was the inverse of the original function f. So let's graph f again. Let's get rid of that horizontal line. And here's its inverse. Now, f of g of x and g of f of x should be equal to x if they truly undo each other. If they undo each other's operations, if you put in x to the composite function, you should get x back. So when I substitute in the inverse function into the original function f, I get x. And when I substitute f into the inverse function, I get x. That's sort of mathematically, algebraically showing that those functions undo each other. Now the claim is that all of this happened because we switched the roles of x and y. And actually, when you think about that, the table of values, like here are a bunch of x values in the domain, and here are a bunch of x values in the range, and these x values map to these y values, these x values map to these y values, and usually it's denoted by arrows. The inverse function just goes the other way. Instead of going from left to right, it goes from right to left. So that's how you're able to undo that operation. But that means whatever was a y value before is now an x value, and whatever was an x value before is now a y value. So if a point AB is on the graph of f, the point BA is on the graph of f inverse. And we can see that visually. We look at y equals x here. Let's graph the point x, f of x naught, label those points. So the point -1 is on the graph of f, 0, 2 is on the graph of f, and 1, 5 is on the graph of f. So if we switch the roles of x and y, we should find the corresponding points in the graph of f inverse. Since 1, 5 is on the graph of f, 5, 1 should be on the graph of f inverse. Since this point 0, 2 is on the graph of f, 2, 0 should be on the graph of f inverse. And -1, -1, if we flip them, we still get -1, -1. If we do that, we see that those points are on our inverse functions graph. So we've done this correctly. And we can create a table of values if we want to. For these x values between -3 and 3, these are the corresponding y values. If we wanted to, we could switch, we could call these our x values and call the x values or these x naught values our y values. And that would give us points on the graph of f inverse.